Welcome to Mastering Solutions. In this problem, it's really helpful to draw a picture first so we can see how many phase changes we have. So we have a thin film, and we'll say that over here this is air, and that has an index of refraction of 1, of course. Now this section here, that's going to be our thin film. So thin film, and that has an index of refraction of 1.38. Lastly, we have glass that the thin film is on, and that has an index of refraction of 1.50. So now as we draw our wavelengths, we can see how many phase changes we have. So light's going to come in first, and since we're going from a lower to a higher index of refraction, we'll get a phase change. And we're going to bend towards the normal because it gets refracted a little bit. And then we're going to hit a low to high. So we'll have another phase change, and that gets refracted in a little bit more. Now off of these, every time it hits, it gets reflected a little bit. So I have one there, there, there. And then these ones are going from a high to a low. So it's not going to have a phase change. Let's go like that. And this one go like that there. So we're going from a higher to a lower. Okay, so we have two phase changes for our wavelength coming through, and then we're going from a high to a low because here is air again. I don't know if we need to worry about that one. Technically, I guess that would be more like that. There we go. Okay, so here's our picture, and we have two phase changes. And because it says here that we want a strong reflection, that means we're going to be looking for constructive interference. So since we have two phase changes and we want constructive interference, we'll be using the equation 2t is equal to m lambda over n. Now in this case, they say what is the thinnest film? And so we're going to look for t for the thickness. And so to do that, we can divide both sides of the equation by 2. So now we have t is equal to m lambda over 2n. Now for the thinnest possible film, we want to use m equals 1 because for this one, if we were to use m of 0, that would give us a thickness of 0, and obviously we can't have a thickness of 0, so for this constructive interference, we have to have an m of at least 1 for this. And so let's write down a list of the information they give us. We should have done this at the beginning, I guess. They say the thin film is magnesium fluoride or magnesium difluoride. That has an N of 1.38. Guess we put that there. And then we have a wavelength, or the lambda is 600 nanometers. And we said M is 1, of course, and the N we have. Okay, so I guess we already had everything. So we have an M of 1 times 600 times 10 to the negative 9 meters, divided by 2 times the n, which is going to be 1.38, of course. So we have 600 times 10 to the negative 9, and that gets divided by 2 times 1.38. And that gives us the thinnest film of 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is going to be 217 times 10 to the negative 9 meters, or 217 nanometers as the thinnest film that we could have that will give us a strong reflection for orange light.